Okie dokie, let's see how this works out. Okay, I'm going to do a little video run through of the solution page for the Module 4 practice test, hopefully getting you ready for the solo test tomorrow. All right, so number one, we've got this crazy looking function here, and I'm asking you three simple questions. F of -1, so you find -1 on the x-axis and you go up to the graph and you get +4. F of 0, do the same thing with a 0, and there you get +2. Find x for f of x equaling 1, so we're looking for a y value of 1, and what x value gives you that. So it's kind of taking the other questions and turning them around. Here is the y value of 1, and the x value that gives me that is 2, so that's why x equals 2. All right, so this is a piecewise function. It's got 3 different pieces, 2 linear pieces and 1 quadratic piece. And the linear pieces do have the same equation, but they have different domains. So I've written them as at 3 different parts. So -x plus 3, if you extended this line down here to the y-intercept, +3, that would be the slope at -1. So -x plus 3, and that graph lives where x is less than -1. I'm assuming that there is an arrow at the end of this graph here, okay? And same thing at the other end. If you included endpoints in your domain statements, you're not wrong. It's just that my graph is a little bit vague. Okay, and then the middle part is this quadratic function, or a parabola. It's got the vertex right there at +2. It actually has a multiplier or stretch value of +2, because from here, if you go over 1 unit and you go up 2 units, you get back to the graph. So it's the a value is 2. So the equation of that is 2x squared plus 2, and that only lives between x equaling -1 and x equaling 1/2. Right there, that's +1/2. So that's your parabolic piece. And then again, -x plus 3, that same equation for x greater than 1/2. So there's your piecewise definition. All right, number 2. The graph of this piecewise function, there's 2 pieces this time. One is a parabola, x squared minus 1, and that looks like this. All right, if it was to continue, it would go right back up like that, but it's got a domain restriction of x less than or equal to +1. So it cruises right along until it gets to x equals 1, and then it stops. And then the other piece is -x plus 1, and that's when x is greater than 1. And that's this line, slope of -1, and if you kind of worked it backwards, it would have a y-intercept of +1. So that's why it looks like that. Graph the function. Okay, this is decreasing on this piece, stopping right there at x equals 0. And it's also decreasing from 1 to infinity. Okay, so that's why we write it decreasing on -∞ to 0 and 1 to infinity. It's also then increasing from 0 to 1. Just this tiny little piece from 0 to 1 is the only place where that graph is going up. All right, that's what increasing means, going up. Decreasing means going down. Last part of this problem is to graph the absolute value of this function. And as you recall, absolute value will just take any negative number and make it positive. That, in terms of graphs, means y values that are negative get flipped into the positive part of our plane. And so this little blip of the parabola below the x-axis just gets kind of flipped right over like that. And this linear piece down here that's going down that way would get flipped to going up at a slope of +1. So this blue thing is what the absolute value of the gray thing looks like. Okay, we're going to flip this over here, and let's see. All right, number 3, absolute value equations. You have to isolate the absolute value part and then set up 2 equations and solve them. Pretty easy there. Do that with a couple of steps first to get to 2x plus 4 equals 7. All right, subtract 6, divide by 2, etc., etc. And then we've got solving those 2 equations gives you 3/2 or -11/2. Same idea over here. Divide by -4 first to isolate the absolute value part, and you get, going through your algebra there, 20/3 or 14/3. And you can use a decimal there if it is exact. This is not an absolute value equation here, part D. You just take the square root of both sides. Don't forget plus or minus, so x equals -2 plus or minus the square root of 5. Alrighty, down to graphing this thing here, this absolute value function, absolute value of x minus 1 in quantity there, -3. So we've got a horizontal shift to the right of 1 unit and a downward shift of 3 units. So that would look like this. All right, this gray V shape right here, with its vertex at the point 1, -3. All right, so we got our domain of all real numbers, the range of -3 to infinity. That's the lowest y value there, going up to positive infinity. My x-intercepts are at -2, 0, and 4, 0. My y-intercept is at 0, -2. It is increasing from 1 to infinity and decreasing from negative infinity to 1. That's we're naming x values there. All right, then the last part, it says create an equation or create a quadratic function that has the exact same domain, range, and x-intercepts. Okay, well, if it's got the same domain, well, all quadratics have a domain of all real numbers, so that's no big deal. If it's got the same range, however, that means it's got a minimum point right there. And so that means then that it must be of this form, this vertex form here, x minus 1 squared minus 3. And there's some stretch factor there that forces the parabola to go through these two x-intercepts, -2 and +4. Well, okay, if it goes through those points, then that means the point 4, 0 is actually on this curve. And so I should be able to replace the x and the y with those x and y coordinates and then solve for a, all right? So we just plug in the x coordinate of 4, 0. We could use -2, 0 also, but I chose 4, 0. And I plug that in here. 0 for y equals a times 4 for x minus 1 squared minus 3. This is 3. 3 squared is 9. And so, oh, by the way, I moved this +3 over there. So I got 3 equals a times 9. And that dividing by 9 gives me an a value of 1/3. So our function is y equals 1/3 times x minus 1 squared minus 3. Okie dokie. Last page. And number 5, find the inverse. Well, you switch x and y and solve for y. Pretty easy there for that linear piece. And so I wrote it 2 different ways. You can write it this way. I kind of prefer this way, but that's just a personal choice. And this commentary about the domain restrictions, it says in the problem, if necessary, restrict the domain from the original function to ensure the inverse is also a function. So we're restricting the domain on the original function, not our inverse. This one is a line. And you don't have to restrict the domain for a line because a line is a one-to-one function and it has an inverse, so I don't have to worry about that domain restriction thing. So we're done with that. Number 2, though, or part B, that's a parabola. That does not have an inverse that is a function unless we restrict the domain. So we could pick either way. We could pick the right hand, or the left hand half of the graph where x is less than or equal to 0, or the right hand half of the graph where x is greater than or equal to 0, and I just chose the latter, that is the right hand half of the graph, x greater than or equal to 0. So now I swap x and y, and I solve for y, and I get square root of x plus 2. Whoa, what happened to the domain restriction? Well, that's all it is, folks. There's really not much to it. I just wrote x greater than or equal to 0. That's my domain restriction for that graph. That means if I'm thinking about the graph, I'm only thinking about the right-hand half of that curve, okay? So it looks kind of like that. And if I was to reflect that across the line y equals x, right, that would go over here to an x-intercept of -2, and my square root curve then would be the positive square root curve. And it doesn't really change anything on my work other than it means that I don't have to put a plus minus in front of the square root sign. In fact, I don't have to put anything if it's positive. So I'm just going to leave it like that. Alrighty, on to the last section, which is right down here. So just performing these operations, okay? This is some number and simplifying radicals practice here, always good to do. Square root of 32, you could write that as 4 root 2. I'll leave you to figure out why that's true, but take my word for it. That's 4 times the square root of 2, minus 2 minus the square root of 2. All right, just distributing that negative sign to inside the parentheses. So I got like terms here, 4 root 2 and minus root 2. That gives me 3 root 2. 4 minus 1 is 3, and then minus 2. All right, so that's my full answer right there. This one, I chose to just multiply straight ahead using the distributive property. So root 32 times 2 is 2 root 32. That's about all I can do. Root 32 times root 2, however, that I can multiply those two numbers together underneath the radical to give me the square root of 64, which, hey, that equals 8. That was nice and convenient, wasn't it? This, since we did say that square root of 32 is the same thing as 4 root 2, see, over there? So when I think of this as 4 root 2, and then multiplying that times 2, that's going to give me 8 root 2. So that's my result right there in perfect, simple radical form. Let's move on to part C, and that's just multiplying these two binomials together using the FOIL method, if you will. Root 8 times root 8 is 8. Got it? Root 8 times root 8 is 8. Then root 8 times negative 2, well, negative 2 root 8. And 2 times root 8, it's positive 2 root 8. Those two things are opposites, and they cancel each other out. And then obviously 2 times negative 2 is negative 4. Well, all I got left is 8 and negative 4. That gives me 4. Ta-da! Last one. I times the square root of 18, quantity squared. Well, that means 18, because the square root of 18 squared is 18, and I squared is I squared, which equals negative 1. So my answer over there is negative 18. Okay, we're done. Hope that was helpful, and we'll talk to you soon. Bye-bye.